So tonight we're going to be talking about a cosmic threat to humanity and what's being done to avoid a civilization-ending event from happening. So specifically, we're going to be talking about NASA's DART mission and what the point of the mission was and what the results were. So just as some background, I'm an amateur astronomer. The moon is my primary interest with its rich history. I'm also a solar system ambassador and one of the founders of the McCarthy Observatory. So if you don't know, the McCarthy Observatory is located in New Milford. It's behind the high school. And we have a mission that is really not necessarily confined to astronomy. We are really dedicated to promoting science literacy and critical thinking. So if you happen to be in the area, we have an open house every month on the second Saturday. So we have one coming up on this Saturday. And if the weather is clear, we have telescopes available for the public to look at the sky. So join us if you can. So back to our program. NASA loves acronyms. So the DART mission, DART stands for Double Asteroid Redirection Test. And it was really a first of the kind mission. We've really never done anything like this. So we're going to take a look at what the objective is, a little bit about the DART spacecraft and where it was going, what it was doing, and what's next. So the objective of the DART mission was to demonstrate one method of moving a body in space, essentially deflecting an asteroid, kind of a proof of concept mission. And of course, there were other ways of moving asteroids, but this one was more of a blunt force method by running a spacecraft into the asteroid and seeing if we could actually deflect it. So the obvious question is, why are we so worried about asteroids? And by the way, what are asteroids? For those who aren't that familiar with the minor bodies in the solar system. So asteroids are bits and pieces of rock. They're left over from the formation of the solar system, which means they're comprised of material that is 4.5 billion years or older in some cases. Most of these space rocks don't pose a threat to us. They're located beyond the orbit of Mars, and they're in relatively stable places. They don't move around much unless they interact with some other body. But as you can see in this animation, and these are plots of actual asteroids, there's a dense cloud of asteroids beyond Mars. And I'm not sure how easy it is to see the screen, but that red line, the outer red line, is the orbit of Mars. So you can see there's a real swarm of rocks beyond Mars out to Jupiter, which is the yellow line. But you also can see there's asteroids inside the orbit of Mars. And Earth is that white circle. So you can see there's asteroids just beyond Earth's orbit and also inside of Earth's orbit. So asteroids come in all shapes and sizes. Most of them are irregular because they are relatively small, so they don't have enough gravity to form a sphere. But you can also see that they're covered with craters. So asteroids tend to have very tortured histories, a history of collisions. So it's not unusual that they would have the markings of such. So Astronomers have identified a little over 1.2 million asteroids in the solar system. Of those asteroids, about 30,000 are classified as NEOs. That stands for near Earth objects, objects that come somewhere near the Earth. And that category is broken down into 3 other categories. And that just means that they have certain characteristics. Some of these asteroids spend most of their time inside the orbit of the Earth. Some cross the orbit of the Earth, and some spend most of their time outside the orbit of the Earth. The real category that we're going to focus on are the PHAs. PHA stands for potentially hazardous asteroid. And you can see there's about 2,300 of those asteroids that have been found. A potentially hazardous asteroid is something that has a certain size, which means it's large enough to do real damage if it hits the Earth, and that it comes within a certain distance of Earth. So something that comes relatively close to us and something that's fairly large, and they will classify it as a potentially hazardous asteroid. And these are the ones that we really want to focus our searches on, ones that pose a threat to the Earth. So why are we that concerned about asteroids? Well, everywhere we look in the solar system, every object in the solar system that has a solid surface and that hasn't been refreshed by some means, we find craters. And those craters have been created by collisions of asteroids. So just in this slide here, in the upper left, that's Mercury. In the upper right, Mars. Lower left is the Earth. That's Meteor Crater in Arizona. In the middle is a radar image of a crater on Venus. And then we have the moon in the lower right. So everywhere we look, not only do we see impact features, but we see very large craters resulting from those impacts. And we see lots of craters, craters upon craters. The reason we don't see many of these craters on the Earth is because the Earth has wind and water and tectonic plates and volcanoes that tend to erase these features. So you can probably find somewhere between 150 and 200 craters on Earth. Most of them are not well preserved and they'd be tough to distinguish. Sometimes we only see them from space. But like I mentioned, the one down in Arizona is probably the most well-preserved crater. And that's about 50,000 years old. So nothing terribly recent, but recent enough. So that brings up another point, is that 30, 40 years ago, we weren't terribly concerned about something hitting the Earth, at least something large hitting the Earth. We kind of got a little bit complacent. But in the early 90s, Gene Shoemaker and his wife, Carolyn, and David Levy discovered a comet that had passed very close by Jupiter. And by passing near Jupiter, the gravitational forces tore the comet apart into many pieces. It was called a string of pearls. There are actually about 21 large fragments. And by studying the orbit of this comet, they realized that in a few years, this comet was going to collide with Jupiter. And that's indeed what happened in the summer of 1994. And a lot of folks kind of dismissed the event, thinking that an object as large as Jupiter couldn't really be affected by a comet. And actually what happened was the exact opposite. And this was something that even I watched in a small telescope happen. But over a period of several weeks, actually it was even a shorter time frame than that, these individual pieces of this comet smashed into the upper layers of Jupiter's atmosphere and created these massive atmospheric explosions. In fact, each one of these collisions produced more energy than all the nuclear weapons on Earth. And they left these visible scars that you can see on the right side of the slide in the atmosphere of Jupiter. And they lasted for weeks until the winds of Jupiter kind of tore these scars apart. But for perspective, these scars, the biggest ones, are larger than the Earth. So there were a massive disruption of Jupiter's atmosphere from this collision. And while we thought it might be a 1 in a million chance of this happening, since then, we've seen several more smaller collisions. We've also seen small collisions on the moon, some collisions on Mars, nothing of this magnitude, but still it kind of a wake-up call that there's still that possibility out there of objects hitting other objects. So are we worried about the Earth? I mean, certainly Jupiter is a massive object. It tends to attract other objects. But, are we safe here in the inner solar system? Well, I've mentioned that there are near-Earth objects that we have to monitor. And the Earth is continually being hit by small, very small objects. Every day, there are small impacts. Most of it burns up through our atmosphere because we are very fortunate to have a very thick atmosphere, but some of it gets through. So if we look at the Earth, of course, we will find craters, and one of the more famous craters is called Chicxulub. It's actually underwater, right off the coast of the Yucatan Peninsula in Mexico. And this crater is 112 miles across. It was discovered by oil company geologists who were sampling the rock looking for oil and gas deposits. And they found this very unusual structure and they started to map it. And when they pulled up the core samples of this area, they found that the minerals in the rock had been melted at a very high temperature, and that there was a lot of shocked material that had been exposed to very high pressures. And it was basically a detective story that came together, and they realized that this was a massive crater underneath the water. And when they dated the crater, it corresponded to the demise of the dinosaurs. Actually, it corresponded to the demise of 75% of life on Earth. So it was a massive event. It was a city-size asteroid that collided with the Earth. There are other examples. One of the more, another famous one is the Tunguska event in 1908. This was an asteroid, or it could have been a comet. We don't know exactly because it didn't leave a crater. It actually disintegrated and exploded in the air over this region, over Siberia. And within seconds, it had flattened 80 million trees over an area spanning nearly 800 square miles. Again, it released more energy, almost 200 times more energy than the atomic bombs we dropped on Japan. Fortunately, there weren't too many people living in this region. There were a few that didn't actually see it happen, but they witnessed a shock wave that happened afterwards. And this rock was maybe only 100, 120 feet across. So you can see the power of some of these collisions that result from even a relatively small object. Another interesting event, and this has just come out a few years ago, was a city, a Bronze Age city in the Jordan Valley near the Dead Sea. And this city had been flattened. I mean, it not only flattened, but this city had been sheared off at the foundations of all the buildings. And all the skeleton remains have been dislocated. Materials in the debris had been melted at very high temperatures of over 3,600 degrees. And again, they found remnants of high pressures that created a diamond-like carbon. And after looking at all the possibilities, including earthquakes and war and fire, the destruction was on the scale, again, of an atomic blast. And the only thing that really fit the model was, again, a comet or a meteor that detonated overhead. So something more recent that you're probably familiar with happened again in Siberia, the Chelyabinsk meteor. And this was on a cold morning in February in 2013. A lot of people driving to work, so they had dash camera videos of this thing coming in. But this is a house-sized asteroid, and it exploded about 14, 15 miles above the ground, and it sent a shock wave that broke just about every window around the area. Very large area, shattered glass, injured about 1,200 people. Fortunately, there was nobody that was seriously injured. But again, it was a big blast of a fairly small size asteroid. But it came in at a velocity of about 11 miles a second. And you can see they pull out a chunk of the offender from a frozen lake. And they found a few smaller pieces. They didn't find a lot of big pieces. These things tend to, when they detonate in the atmosphere, they break up into a lot of small pieces. Just one last example, and this is interesting. This was an asteroid that had a close encounter. It passed and crossed the orbit of the Earth on November 1st. And it was somewhere between 1,000 and 2,500 feet. It was moving at a velocity of 52,000 miles per hour. It didn't come terribly close. But again, you know, the Earth is moving, the asteroid's moving. So sometimes there are relatively large misses. But I think the important thing to look at here is that last line. This asteroid was only discovered on September 12th. So we only had 6 weeks of warning. If that had been on a collision course rather than a miss, we wouldn't have had much time to react. So that brings up the next thing. And the most important thing is that if we can't find an asteroid, then we can't prevent it from hitting us. So it's very important that we are on the lookout, that we are able to find these potential hazards, and the earlier we find them, the better. Fortunately, over the past, I'd say, 30, 40 years, there's been a greater interest in looking for these objects. So now there are facilities dedicated in Hawaii, in Arizona, in the Southern Hemisphere, that spend their nights scanning the skies, looking for objects that are heading towards us. And on any given night, they can identify maybe a dozen potential objects. So they identify a potential object and then they move on to scan the sky. And what they do is they send their observations down to a central clearinghouse. And this is the Minor Planet Center. It's in Cambridge, Massachusetts. And the Minor Planet Center acts as a clearinghouse. They collect all these observations. And again, these are only potential new discoveries. So what the Minor Planet Center is doing is it's putting out this information to places like the observatory in New Milford or observatories all over the world. They're saying, here are some new discoveries. And what we need to really refine the orbit, we need a lot more observations. People who discovered the asteroids have moved on. They're doing more observations of the sky. So they're looking for people to follow up places like the observatory in New Milford, do additional observations, and we can, every observation they get, every additional observation, they can refine that orbit of that asteroid. And so maybe what starts out as a really hazardous asteroid on first look, after a week or two of observations, it's a no, never mind. It's not going to come anywhere close to us. Or it could be the other way around. So when we see objects that are within our range, and we can track some pretty dim objects at the observatory. We can see things with our cameras that are 1,000,000 times dimmer than the human eye. We can't see objects that are really small and faint, but we can see some pretty good size asteroids. So what we would do is we would observe it over a night or maybe 2 nights or 3 nights, and we would send in our observations to the Minor Planet Center, and they would use that to refine the orbit. So since 2000, when we opened up, we've submitted over 2,000 observations of near-Earth objects that have been accepted by the Minor Planet Center. And one of the ones that this slide is focused on is Apophis. Apophis is an interesting asteroid. It's called Apophis the Destroyer. It was discovered in 2004, and it is classified as a potentially hazardous asteroid. It's a mixture of metallics and stone. It's a real composite from as much as we can tell. And we've radar imaged this asteroid because it has come quite close to Earth. So places like Arecibo, which is a big radar facility down in Puerto Rico that's no longer with us, they were able to get a rough shape and size of this particular asteroid. So it's over 1,000 feet in width. So it's a fairly good size object. So it could do quite a bit of damage. And it does cross the Earth's path. So the reason this is particularly interesting, and the reason I was down at the observatory last year taking more images of it, was that in 2029, on April 13th, it's a Friday the 13th, in 2029, this asteroid will pass within 20,000 miles of Earth. So that is closer than a lot of the communication satellites that are in orbit around the Earth. So there's a lot of concern with the accuracy of the orbit and how close it was really going to come. So that's why they were looking for additional observations. So this is the observations from last March, and hopefully it's not going to crash my presentation. But you can see the asteroid moving among the stars. And if you combine all those images, you get this series of dots that shows the asteroid's position at 5-minute intervals. So that's what we do, is we take multiple images, and then when you combine all the images, the stars don't move relative to our view, but the asteroid is moving among the stars. So the other thing we need to do with asteroids is we need to know something about it. They come in all different, I'll call it flavors. But if you're going to push an asteroid or move it out of the way, you need to know what it's made out of. You know, if it's rock, if it's metal, if it's loose, if it's solid body, if it's one, or asteroids come in pairs sometimes. So we have sent out several missions to visit asteroids and get a better feel for what we're dealing with. And one of the missions was OSIRIS-REx. Now, this is an ongoing mission. It's a sample return mission, and it visited the asteroid Bennu. Bennu is a potentially hazardous asteroid. We tried to sample it. We did sample it. We collected some of the surface material, but the real surprising thing was that when we touched down on the surface of the asteroid, our sampling device sunk right into it. It was like it was a ball pit. It was a pile of rubble. Totally unexpected. Looks like a solid body when you look at it from afar, but it turned out to be a lot less solid than we expected. So something to know when we're dealing with some of these bodies. You know, for perspective, this asteroid's about 1,600 feet across. A potentially hazardous asteroid is anything larger than 500 feet. So it certainly falls into the category of large enough to do damage. Another mission that is ongoing right now is Lucy. Lucy is on its way out to visit a number of asteroids. It's actually going to visit 8 different asteroids over a 12-year mission. And these asteroids are called Trojan asteroids, and they share an orbit with Jupiter. They either orbit in front of Jupiter or behind Jupiter. And they are believed to be very, very old, probably asteroids that have been around since the very beginning of the solar system, and therefore they offer us a glimpse of what the conditions might have been. So Lucy is it's the name of the mission is associated with the Lucy fossil that was found in Ethiopia as far as the dawn of man. And it's also associated with the Beatles song, Lucy in the Sky with Diamonds. So interesting mission. Again, it's a 12-year mission and it's just started out. So it's going to be a while before we start seeing results from there. Next year, we're going to be launching a mission called Psyche. And Psyche is going to the asteroid called Psyche. And while Psyche is not a hazardous asteroid because it orbits way out at the edge of the outer edge of the asteroid belt, it is potentially a very different type of asteroid. In fact, some people think that Psyche is the core of a small planet that was destroyed billions of years ago, and that all that's left is the center of that object. And as such, it has a very high metal content. So there's a lot of disagreement on how much metal content is in this asteroid, but it's something we're going to find out when the spacecraft gets there. But again, it doesn't launch until next October. You can see the spacecraft on the right in the clean room, getting prepared. Actually, that's my daughter in the foreground there. So, assuming we can find these asteroids that pose a threat, what do we do next? Well, it really comes down to how much time do we have. If we have a lot of time, we have a lot of options. There's all kinds of ways to kind of tweak the path of an object if you have time, because it doesn't take much tweaking when the asteroid is years away from hitting you. The asteroid was only discovered 6 weeks ago. You have very few options. So that's where the DART mission comes in. The DART mission was a demonstration mission of one technique called kinetic impact, or basically smashing into the asteroid and seeing if you can move it. It was launched just about a year ago. It traveled several million miles before it got to its target. And its target was a binary asteroid, which means there were 2 asteroids involved here. And the primary asteroid, the larger asteroid, was called Didymos. Didymos orbits the sun roughly every 2 years. And at its closest point to the sun, it intersects the Earth's orbit. So you can see I'm using units of measurement called AU, and that stands for astronomical unit. 1 AU is equal to the distance of the Earth to the sun. So you can see at its closest approach, it is at 1 AU, which is the distance the Earth is. So as I mentioned, this is a binary asteroid. Didymos is we'll call it the parent or the primary, and it has a small moon called Dimorphos. And really, Dimorphos was the target for DART. The objective was to have DART collide with Dimorphos and to see if we could change Dimorphos's orbit. This was all being done about 7 million miles from Earth, so there wasn't any hazard to the Earth. We're also going to carry along with us a CubeSat, a small satellite that would be released before impact, and it would monitor the impact to see what happened, because we're going to destroy the spacecraft. The spacecraft is going to run directly into Dimorphos. And we were going to do this close enough to the Earth so that the telescopes on Earth could see it, so that we could have all our eyes on the collision and the results. So these are the 2 bodies. Didymos, the larger one, about 25 feet across. And you have Dimorphos, which is considerably smaller, only about 525 feet across. So before DART arrived, Dimorphos revolved around Didymos once every 11.9 hours. And NASA was hoping by this demonstration to change that. So the DART spacecraft was a fairly low cost, stripped down model. Had 2 solar arrays for electricity. The only payload it was really carrying besides that CubeSat was a camera. And the camera served multiple purposes, but that was the primary navigation instrument. So there's a picture of the CubeSat, about the size of an old lunchbox. And that's the object that would fly past the two asteroids and record the impact. They were going to deploy it about 15 days before the impact, and it would fly behind the DART spacecraft. The DART spacecraft did incorporate a number of advanced technologies. It used a new generation of ion thrusters, and these are very efficient thrusters that accelerate electrically charged atoms. And while they are very low thrust, they operate continuously, so they keep building up until they get to a very high velocity. They also installed a new high gain antenna, that round dish looking structure. And the interesting thing about this antenna is it can receive and send data simultaneously. Now this is the spacecraft. You can see it's not very large. And if you notice, on each end of the spacecraft are those yellow striped rolls. Those are the solar panels. That's another technology. Those solar panels were rolled up. And to demonstrate the technology, they installed one on the space station, and they demonstrated that they could roll it out. So once the DART spacecraft got into space, the solar panels on each side of it basically unfurled. And this saved a lot of room and a lot of weight, actually. So, Big Bang all happened on September 26th, when the DART spacecraft impacted that small little moon at almost 15,000 miles an hour. And as I mentioned, this happened about 7 million miles away from Earth. And the Italian Space Agency made the CubeSat, and that followed behind about 600 miles behind the spacecraft. But to give you an idea of the precision, they were able to impact that small moon about 50 feet from the center point. Pretty high precision given the distance that spacecraft traveled. It was pretty amazing. And how fast everything is moving. When you think about it, that spacecraft was moving about 4 miles every second. So what happened here was that we couldn't see the moon from Earth. So the spacecraft was focused on the larger object. So as DART got closer, and this happened all within a few hours of impact, DART was able to recognize, using this new smart navigation system, it could recognize which was the larger object and which was the smaller object, and able to redirect its trajectory towards the smaller object. So you can see this is some still frames that were put together into a movie. As DART approached, it's going to pass Didymos and head for the smaller moon. Some of this is speeded up, and as we get closer, some of these images are more real time. But now you're starting to see the surface and the structure of the moon. And then the camera, of course, cuts out once it's been vaporized. So the Jet Propulsion Laboratory provided the trajectory towards the larger object, and then the spacecraft operated on its own as it got closer. From Earth, you couldn't see the moon, but you could see the larger object traveling, and then you see it blow up. You see a very large brightening of Didymos, the larger one. Then you see this cloud of debris, which is coming from the moon, which you can't see. So this is just a repeat, but you can see how the debris is cast off. And the surprising thing was how much debris and how long the debris trail was. The debris trail from this collision was thousands of miles. And we had the Hubble and we had the James Webb watching this event, and they both noticed a large brightening of the object shortly after the collision. Now, here's an image here from the CubeSat. So the CubeSat, of course, the resolution is not as great. You get a very small camera on a very small object, but you can see the larger body, Didymos, pretty clearly, and the smaller body is kind of hidden in a cloud of I guess it's a cloud of debris that's been kicked off by the collision. So what did we learn from this? Before DART arrived, Didymos's orbital period was 11 hours and 55 minutes. After the collision, the orbit was shortened by 32 minutes. NASA had defined a minimum success standard of about a minute or 73 seconds. So this is well beyond what they could have possibly imagined. 32 minutes rather than a little over a minute. So the asteroid actually moved in closer to the larger one and shortened its orbit by 32 minutes from that collision. So how do we know this? Well, there were two ways of doing this. One, we got some direct images from these large planetary radar facilities, one in California out at Goldstone and one in Green Bank, West Virginia. So they could image directly these two objects. And you can see on the screen, the green circle is Dimorphos, the smaller moon. The blue circle is where it would have been if it had not been hit. So you can definitely see it's not where it was supposed to be, and that's due to the collision. The horizontal light band, really bright light there, is the main asteroid there, Didymos. The other way we could figure out the change is by measuring the light. As the smaller moon passes in front of the larger asteroid or behind it, you get a dip in light. It's either the small moon is blocking light from the larger one or vice versa. And you can measure this light delta and figure out the orbit of the moon. So that's how they figured out the 32-minute change. So that's, we know quite a bit, but we don't know everything. So fortunately, the European Space Agency has a mission coming up called Hera, and Hera launches in 2024. It's actually flying out to Didymos and Dimorphos. So it's going to fly out and orbit these two asteroids. It's going to characterize these asteroids, find out what they're made of. But more importantly, it's going to find out what kind of damage we caused to that small moon. The crater, did we disrupt it significantly? Why did we get so much debris off the small moon? So Hera is going to be very important to complete the picture. It's one thing to smash into an object and make a change. Hera is going to give us some answers onto why that happened or why there was such a much larger change than we expected. So to sum it up, DART mission really marks the first time that we intentionally changed the motion of a body in space. The real first full-scale demonstration of one way of changing an asteroid's trajectory. And of course, this is particularly important should we identify objects that pose a direct threat to Earth. Down the road, we're working on some other projects. We have a space telescope that is in the developmental stage. It's past the critical review stage. It's waiting for funding and for a final okay before it gets built and launched. But it's going to be able to survey the sky from a point between the Earth and the sun. And this is important, and we'll get into this in a second, but this is important because this is an area that's not very well characterized. It's very difficult to look towards the sun. It's easy to look away from the sun and find objects. But when you're looking at this very glary, object, very, very bright, it's difficult to make out smaller objects. So the NEO surveyor will be looking in front of Earth's orbit and behind Earth's orbit for objects that we might not have seen because of the sun's glare. We're going to get a sample back from OSIRIS-REx next September. So this is the sample container. It contains what we believe is a fairly good sized sample of the asteroid's surface. And that sample container will be dropped off as the spacecraft flies by Earth next September. The interesting thing is that NASA has already figured out they're going to repurpose this spacecraft. So once it drops off the sample, it's going to send the spacecraft to intercept Apophis. So when Apophis flies by the Earth on Friday the 13th, 2029, the OSIRIS-REx spacecraft will be there to meet it and be able to get a real good opportunity to characterize what Apophis is actually comprised of. We're also building some new facilities on Earth. And one of these observatories is down in Chile. And it is a very large telescope with a very large camera. And it's going to be able to measure the properties of several million moving objects. Again, we're looking for objects that are moving. The stars don't move once you have the proper tracking. This particular telescope is going to be able to find asteroids as small as 500 feet, which is really the threshold of where they start doing damage if they happen to collide with Earth. So to conclude this talk, not to get people terribly worried, but we mentioned objects that come out of the sun that we don't have the ability to track yet. Just on Halloween, one of the headlines, or actually the headlines in many of the newspapers and online media, was that there was a new asteroid found that was hiding in the sun's glare, and it was a potentially hazard asteroid. So we did find it, and it doesn't pose an immediate threat, but it gives us fair warning that these objects are up there, and they do have the potential to interact with the Earth at some point in the future. So I appreciate your time tonight. I don't know if anybody got up nice and early this morning, but this was a photograph from my driveway. We had a beautiful total lunar eclipse this morning. So if you didn't have an opportunity, this is a photograph of what was as the moon slid into the Earth's shadow. Unfortunately, we're going to have to wait another almost 2.5 years before we get the opportunity to see another one. So thank you.